Hi everyone, I'm here to present our research paper, The Motion is the Message, Evaluating Motion Tracking Quality for VR Avatars. This research is sponsored by Meta Reality Lab, and the authors are me, Fusha Yang, Dr. Smith, Dr. Moses, and Dr. Neff, researchers from both Purdue University and UC Davis. To provide the background of this study, in embodied virtual reality, users' avatars can move accordingly to users' motion based on the HMD tracking. While the tracking and reconstruction algorithms are improving through extensive research and the enhanced hardware devices, which equip with additional onboard cameras, we still see errors where avatars' movement are not 100% accurate, which make the evaluation of HMD-based motion tracking important. In avatar motion evaluation, we often see quantitative measures such as motion speed, trajectory, jerkiness, or the pressure gesture distance. As for qualitative instruments, they usually include perceived naturalness, appropriateness of gesture timing, and the Gauss-Speed questionnaire, which covers the human likeness, likability, and perceived intelligence. However, past research have shown that quantitative results often correlate poorly with human perception of the motion. Hence, our work targets the current research gap to evaluate the preservation of social meaning in HMD-based tracking motions. We want to evaluate motion by measuring its content. In social settings, motion is often providing particular nonverbal communication. We measure whether those nonverbal signals are received by participants as a way to measure fidelity of the motion. Our research objectives include proposing a social signal-grounded evaluation benchmark, perform the evaluation on selected HMD tracking algorithms, and share our insights through our results. So here is our proposed motion scale as evaluation benchmarks. It's designed to vary specific social signals at multiple levels. We created 6 bipolar signal scales from attractive versus repulse to positive versus negative, as you can see in the table here. Each of the signal scale is performed at 5 levels from one extreme to the other. Next is the 2 posture scale. First is the arm posture, which varies the arm swivel angle, essentially how close the shoulders and elbow are held into the torso and outward. The second is the posture range, which varies the spine and collarbone flexion from collapsed to overly erect with 7 levels. And last is the emotion scale, where 2 intensity levels were designed for each emotion. And that gives us a total of 52 motions in our motion scale. We intentionally choose scales so that collectively they exercise different upper body regions so that failures can be localized to particular parts of the reconstruction. This design scale was intended to use for communicative social interactions, so we focus more on upper body motions compared to lower body motions. And here is our motion capture session.
We first worked with actors to build a series of motion scales based on different social signals.
I can't believe you did that.
Performances were recorded simultaneously with marker-based motion capture and HMD cameras, allowing the same motion to be solved using both motion capture and 2 HMD tracking algorithms, HMD1 and HMD2.
After the motion capture session, we got 3 condition clips for each motion. A crucial detail here is that the motions are recorded simultaneously for mocap and the HMD streams, which means that the performance motion is the same across all 3 conditions. So if there's any perceptual differences, it's observed from the reconstruction and not from the differences in the actor's performance. Mocap is the optical-based tracking results through OptiTrack system. HMD1 refers to the Meta's Movement SDK, the full body synthesis FBS reconstruction, which is viewed from the headset position and hand tracking. HMD2 is the enhanced reconstruction, the Movement SDK's IOBT, inside-out body tracking, which leverages additional onboard camera streams to output a higher fidelity body tracking results. Here is the procedure of our study design. We first conduct our mocap captures with 5 different professional actors. It's a way to decrease bias from a singular person's motion source. And after that, all motions were processed and played on a neutral avatar to avoid any perception bias from avatar's gender, age, or appearance. After that, we conducted an online selection study where we combined all the recording clips from the 5 actors and presented them separately to 30 participants through Mechanical Turk for each scale. Participants were asked to rate the motion social signal and naturalness at a 7-point Likert scale. We then picked the clips in each scale that best spanned across the social signal ratings and were evenly spaced. The naturalness ratings were used as a filter to remove any highly unnatural clips. The selected clips were then used for our final VR study. In our VR user study, we had 62 participants. Each participant were asked to view a total of 156 clips, which are the 52 selected motion rendered in 3 conditions. Participants were asked to take breaks to reduce fatigue during the session. And after viewing each clip, they were prompted to rate the perceived social signal ratings and the naturalness of the motion, also at a 7-point Likert scale. For the emotion clips, participants first categorized which emotion they thought was being expressed, and then they rated how confident they were in the choice and how intense the emotion appeared and also the naturalness. Here is a quick glance of the results in each social signal scale. The asterisk indicates the HMD clips that perform significantly different from mocap. The plus sign indicates HMD clips that perform significantly better in naturalness than mocap. And here's the result for posture scale. Let's take the arm posture range as an example. As we see, the blue indicates motion from mocap, which is following the design posture progression from very shy to very dominant arm posture range. And here, as you can see, HMD1, which is colored in red in the chart, it shows significant differences in the social signal ratings from the mocap as baseline, which indicates the discrepancy in conveying the correct social signal under the shy, the neutral, and very dominant level in the scale. And here's the emotion scale. I would highly recommend to look into more detail in our paper. So let's talk about the statistical results. Since our core assumption is that a tracking method succeeds if it faithfully preserves the message in the user's motion. So we treat mocap as our ground truth, meaning that whenever an HMD result is perceived significantly different from mocap, we consider that a tracking failure. We analyze the ordinal Likert responses using cumulative link models, and finally, we compute 2 summary scores. First is the failure count, representing how many motion clips are significantly different from mocap. A second is the magnitude score, which is the sum of effect size across significant differences using the Cohen's-d value. And here's the summary of our results, starting with the social signal ratings. Here in the table, HMD diff represents the failure count in each scale category. DT is the total effect size of Cohen's-d, and DM is the mean. The result shows that HMD2 preserves social meaning more accurately than HMD1, with a lower rate of significant differences compared to mocap at around 40%, and the HMD1 is at 53%. The total effect size is also lower in HMD2. However, naturalness tells a totally different story. We compare naturalness ratings for each HMD against mocap. Here, HMD1 or HMD2 worse better refers to the motion clip counts, which are rated significantly worse or better compared to mocap. You will notice that there's no HMD2 motions that were rated significantly more natural than mocap, but around 9% of the HMD1 clip are rated as more natural than mocap. Although both HMD1 and 2 are frequently rated less natural, with HMD1 at around 78% and HMD2 at around 94%. This helps explain an important point. So social signal accuracy and naturalness can diverge. HMD2 tends to prevent the social message better, but it can introduce some constant jerkiness due to additional body tracking inputs. However, in HMD1, in the contrast, sometimes it appears smoother and therefore more natural because it misses part of the motion, which may express the accurate social signals. So a motion can look more natural while conveying the wrong social signal, And emotion can also convey the right signal while looking less natural. The divergence is central to our argument that we need both measurements, and that social signal preservation should be evaluated directly. We also conducted a qualitative review of clips through camera footage of the mocap session and inspected what changed in the reconstruction and make possible connection to the perceptual rating. And here we identify 3 main categories. The first is arm tracking issues.
Dominance is reduced by the failure to capture the swivel angle of the arm in HMD1 and the shoulder raise in HMD2. In the relaxed clip, we can see arm jitter in HMD2 that makes it look less relaxed. The SAD clip produced recognition errors due to the difficulty of tracking gestures close to the body.
Second is the posture reconstruction issue.
Coronal posture changes failed to track in the happy clip. Subtle sagittal posture changes are missed in the limp posture clip. For the very tired clip, we see errors in sagittal posture, shoulder angles, jerk in the arms, and a failure to capture a low gesture. HMD tracking fails to capture a relaxed lower body stance.
And the third is the floating issues.
In the very disinterested clip, we see head motion generates body rotation and floating. For HMD1 in the interested clip, a forward lean becomes a forward translation. HMD2 also has some floating and fails to correctly reconstruct the collarbones, but the motion still reads correctly.
So to put everything together, most importantly, our finding shows that naturalness does not always align with social signal accuracy. This divergence is a key finding, emphasizing that realistic and natural motion does not automatically guarantee correct social communication. Overall, our conclusion is that in social VR, motion tracking quality should definitely consider social signal preservation quality. Motion is the message, and preserving that message must be the standard in evaluation. Thank you for listening.